Welcome to Alaska Earthquake Science Facts. I'm Carl Tate. Station COL in Fairbanks, Alaska was installed in January 1964, just in time to record the magnitude 9.2 earthquake in March. COL was one of 2 stations in Alaska and one of 94 stations in the worldwide standardized seismograph network. This is a map showing the 2 stations in Alaska at the time of the 1964 earthquake, one in Fairbanks, 450 kilometers from the epicenter, and one in Sitka, 800 kilometers away. So this will motivate a discussion here about the evolution of seismic stations in Alaska. In Alaska, the seismic stations at Sitka and Fairbanks followed the establishment of magnetic observatories for monitoring space weather. What's shown here are the 13 magnetic observatories of the US Geological Survey. Sitka is shown here. CMO is the College Magnetic Observatory in Fairbanks in the woods north of campus. And here's a picture showing Sitka, home of Alaska's first seismometer, which was installed at the Magnetic Observatory in 1904. From a 1942 paper, we can get some history of the Sitka Magnetic Observatory. This is showing the Variation Building and Old Russian Blockhouse, 1903. And a few notes on this. Sitka was the Russians' Alaska capital starting in 1808. Sitka served as the US government capital of the Department of Alaska 1867 to 1884 and District of Alaska 1884 to 1906. It was purchased from Russia in 1867. And this caught my attention. This blockhouse shown on right is a restored blockhouse outside the UAF Museum of the North, and it looks very similar to this one shown here at the Magnetic Observatory, and kind of a reminder of the time, the era from purchase of Russia in 1867. Not surprising to see, even in 1903, some remnants of this cultural connection. Here's the Sitka Magnetic Observatory Variation Building, 1902 to 1940. First started recording in 1902. The priority of the observatory at Sitka was recording variations in the magnetic field, not recording variations in ground motion. But in April 1904, quoted here in this 1910 paper, a seismograph consisting of 2 horizontal pendulums was mounted in an addition to the astronomic observatory. And here's the first station log of earthquakes recorded in Sitka. What it is basically a number of each earthquake and the time that each waves arrive, the preliminary tremors, second tremors, the large waves, end of the principal motion. So it's telling you when they arrived and what the size is. And as a side note, only 3 months after it was installed, it recorded one of the largest earthquakes ever to hit mainland Alaska, which is a 7.3, kind of in west central Alaska, August 27th, 1904. You can see from the amplitude, everything's about 0.1 millimeter, and then all of a sudden there's a 55 millimeter swing on the north and the east component here. The second seismic station in Alaska was installed in the University of Alaska campus in 1935. This is a figure taken out of a seismological journal showing the northernmost seismological station in North America. And this is the Eielson building, which is probably not familiar to students today. And I'll show you why here. Superimposing the Eielson building today, you can see there's some additional floors built on it. This is what the building looks like today. If you go back, see it's got the same solid foundation and entry as it did in 1935. Importantly, what was housed in there, seemingly from the start of the opening of the building, were these 2 seismometers shown here in that same 1936 paper. So there's a seismometer, second seismic station in Alaska. Fast forward 1945, the Trinity Test, and we'll see why this nuclear test led to the improvement of the seismic station in Fairbanks. This is a paper by Bino Gutenberg, who looked at the recordings of the Trinity Test on seismic stations in the lower 48. He's a seismologist at the California Institute of Technology. And what Gutenberg wrote in this short paper regarding the origin time, he says the time of the explosion is known only to within about 15 seconds. And later he says an origin time of 11:29:21 was used in the following calculations. It is probably correct within 2 seconds. So Gutenberg is here saying, we don't know what they said about the origin time, but we can tell you from the recordings on seismometers, accurate to within 2 seconds. So this foreshadowed the benefits of seismic stations for nuclear monitoring in this first test, followed by a paper less than a year later. In the history of seismology, a paper by Duncan Agnew, I won't read this whole thing, but some highlights in red here. The first nuclear explosion in 1945 was detected seismically. We saw that. With the pressure to move testing underground, seismic methods became more important. And this led to some government investment in seismology and instrumentation. The last portion saying here, Vela Uniform's most important instrumental contribution to seismology was certainly the worldwide standard seismograph network. This provided seismologists for the first time with easy access to records from standardized and well-calibrated sensors spread around the world. This shows a map of the worldwide network of standard seismograph stations. And your eye may be drawn to things like the absence of any stations across the Soviet Union. This was driven primarily by Cold War between US and the Soviet Union. And so there are no stations available to users in that portion of the world. There's also not a lot of stations in Northern North America for other reasons. But what you can see here is that college on University of Alaska or in Fairbanks occupied a kind of key portion of the world. If you're looking to characterize the activity for an event, you want to kind of have as good coverage as possible of the planet. So you can see that this station would have been rather important given that it was the only one for a long ways around it. So you can see the importance of the positioning of geophysical instrumentation in Fairbanks. This shows the technology used in the stations at that time, state of the art. Components of this network system, long period seismometers are shown in the upper left here. Galvanometers and recorders are in the lower left. Short period seismometers shown in the upper right, and the recorders, galvanometers in the lower right. And this is the electronics console power supply. So this shows the kind of instrumentation that would be housed in the COL Fairbanks vault in 1964 when it was installed. This is what photograph taken from the site in 1964. So the original picture of the 1935 station was housed in a building on campus. As you can imagine, with all the commotion and noise of a campus setting, especially in a building, you're not going to be able to detect the quietest signals from recorded on the other side of the planet. So this was a major upgrade in designing a custom vault. It looks like a bunker made out of concrete. This is very close to bedrock, so it's a very strong connection between where the seismometer sits and the Earth itself, and that leads to a better overall quality of the station. So this was installed January of 1964. This photo not taken in January, clearly, but showing a very early building of the vault. And this shows the record of the 1964 Alaska earthquake, magnitude 9.2, second largest earthquake of all time. And this is showing the recording for the closest sensor in the world, which was 450 kilometers from the epicenter. Not surprisingly, with the size of this earthquake and the time period, the main recording just knocked the sensor out of balance and did not record anything in this first day after the shock. But I'd say even today, when we look at large earthquakes, we often take instrumentation that's far away from the event to understand the characteristics of the earthquake. Today, for example, at the COL seismic station, there are different instruments specifically designed to handle what's called strong ground motion. But even at the time, although the main shock wasn't recorded at the station, aftershocks were recorded. This is the following day showing Normal modes, meaning the Earth has basically been ringing like a bell and picking up these large-scale oscillations. So this station was back up and running shortly thereafter. So here we are, 1964. There are two seismic stations in Alaska, Fairbanks and Sitka, and we'll see the evolution of this in the ensuing decades. By 1980, there's a lot more seismic stations, heavily clustered in the coastal region. Fast forward to 2014, and we see what the network looked like, primarily surrounding some of the roads. So this is the one road going from Fairbanks to the North Slope. And there are the Richardson Highway, Parks Highway, and some of these are remote areas, certainly in this area clustered in southeastern Alaska. And this is 2018. So this is the impact of the EarthScope seismic array nationally funded experiment. And we can see just the spectacular coverage that occurred between 2014 and 2018. So here's 14 and 18. And we'll be talking about the instrumentation associated with each of these sites in a later fact. But here, at the moment, there's large numbers of stations in remote regions of Alaska. Some of these are expected to remain there permanently. Others will probably go away. But it was a huge expansion in that 4-year period. Takeaway topics for 120. Earthquakes have been recorded by seismometers in Alaska since 1904 with the first station in Sitka. The second station in Alaska was installed on the UAF campus in 1935. In 1964, it was upgraded and reinstalled on a ridge northeast of campus as one of about 100 high-quality stations of the worldwide standardized seismograph network. This network was supported by U.S. national security efforts to monitor global nuclear explosions. From 1964 to 2014, seismic station coverage in Alaska reached most road systems and regions having existing power sources. The EarthScope seismic array 2014 to 2021 provided semi-uniform coverage of high-quality stations across Alaska. And finally, there's no such thing as a permanent station. It takes constant funding and commitment to keep these data streams flowing for the sake of operational settings for the public and also for scientific discovery. Thank you for watching. Stick around for supplemental material. This last slide describes the kind of technology used in 1964 to make the recordings shown at right from March 27th, 28th, 29th, and you get some idea of the technology at the time. This is no longer in use, but it's interesting to see what it took to record these earthquakes in that era.